Hi, welcome to OpenARK's ISMAR 2022 tutorial. My name's Adam, and today I'll be giving an introduction into three key concepts in AR, VR, and 3D computer vision: SLAM, 3D reconstruction, and digital twin. OpenARK is an open-source augmented reality SDK that will allow you to rapidly prototype AR applications. It was founded at UC Berkeley in 2016 with the mission of offering core AR functionality to developers for a multitude of devices. You can view our project website at the first link, and the source code is available at the second link to put to use in your own projects or contribute. On the right is a picture of my research partner Moonwan and I at the Jacobs Hall Berkeley Winter Design Showcase. Some of the core functions forming the foundation of AR/VR today are listed below. At OpenARK, we have developed and are currently developing systems to provide each of these functions. Today, I'll be focusing on three of the functions that OpenARK provides or aims to provide going forward: camera localization, 3D reconstruction, and 3D object tracking. First, SLAM. SLAM stands for simultaneous localization and mapping. Localization refers to the process of determining the current position of the camera with respect to some representation of the world. Mapping refers to the process of generating a representation of the world from a sequence of camera frames. These two problems are deeply intertwined. Some of the largest advances in industry AR/VR are powered by advances in SLAM. Of note are standalone VR headsets and in-picture AR mobile applications such as Google's 3D Object Viewer and Pokemon Go's AR Plus Pokemon capturing scene. What they share in common is the ability to anchor virtual objects into reality. This requires a frame-by-frame estimation of the camera's position at all times. The algorithm behind this is SLAM. Simultaneous localization and mapping, SLAM, is the computational problem of constructing or updating a map of an unknown environment while simultaneously keeping track of an agent's location within it. The GIF on this slide illustrates an example of a visual SLAM, which uses RGB and depth images from a video feed to track a camera's 6 degrees of freedom pose over time. The 6 degrees of freedom refer to XYZ position, pitch, roll, and yaw, rotation. Notice the yellow dots in the video feed. These are called key points, and they are vital to the operation of visual SLAM. In general, a SLAM framework is built with the following 4 steps. First, we initialize a map of landmarks. By landmarks, I'm referring to 3D key points and their associated features. Second, we receive a new key frame from the camera and estimate the change in position and rotation of this frame compared to a previous frame. Next, we extract the landmarks from this new frame and add them to our map. Finally, we optimize the pose estimation and optimize landmark positions in our entire map. This process can continue indefinitely, and the map continuously expands as new frames come in. So, what are the building blocks of SLAM? Today, I'll be going over a few key building blocks that allow SLAM to work. First, key points and descriptors. Second, transformation estimations. Third, our map representation. Fourth, loop closure. And fifth, alternative sources of data, such as inertial measurement units. Key points, or features in the case of SLAM, are specific points in an image that satisfy these key conditions, allowing them to be used for SLAM. They are usually corners or pieces of patterns that can be identified and tracked with ease. They need to be salient, meaning they are unique points detectable from different positions and different image frames, and able to be matched between frames. This means that if I take an image of a building from one angle, reposition and take an image of the building from the same angle, I should be able to find key point pairs between the two frames. They need to be describable, meaning each key point needs a unique label. Creating this label is what transforms the point from a key point to a feature. One desirable quality is that the key points should be rotation and scale agnostic, as rotating the camera or moving further or closer from an object should not influence whether a key point is detected and matched to itself in a previous frame. Lastly, they need to be of relatively small quantity, as brute force key point matching requires n-squared time, checking each key point in a new frame against every key point in a previous frame. Here are two examples of key point descriptors and descriptor extractors. On the left is SIFT, short for Scale Invariant Feature Transform. SIFT is an earlier form of scale and rotation invariant feature extraction, developed in 2004. It first detects potential key points using sliding windows of different scales. It then assigns an orientation to the key points based on a summary of the neighboring pixels. Finally, a feature descriptor is created from a 16 by 16 pixel area surrounding the key point. BRISC, otherwise known as binary robust invariant scalable key points, is a more recent algorithm, achieving competitive or sometimes better results, but with faster computation time. The image on the right depicts the sampling pattern that BRISC uses for generating a feature description. In their paper, they report a 3 times speed increase when finding correspondences between two images over older algorithms. Correspondence matching, being one of the most intensive portions of the SLAM algorithm, means this speed increase is greatly appreciated. Key point detection and description is one of the most important parts of SLAM, as they form the foundation of a SLAM algorithm's understanding of the environment. As such, part of this year's OpenARK team's work focused on testing different key point algorithms. We explored ORB, oriented fast and rotated brief, an improvement to an earlier key point named fast that incorporated multi-rotation and multi-scale components. We also explored some deep learning solutions such as R2D2, DISC, and Superpoint. However, we didn't find a compelling case for switching to deep learning features, as their performance gain was not definitive and the performance cost was very high. Once we have these key points, we can perform key point matching. Using correspondences between two different images, we can now move on to find the transformation between these two images. The next key concept required for SLAM is frame-to-frame pose estimation. Pose, or transformation estimation, refers to the relative translation and rotation between two image frames. The transformation estimation is performed using key point correspondences between any two frames. This is an optimization problem and can be solved in different ways. At its most basic level is the perspective and point algorithm, which, given a number of key point correspondences between two frames, can estimate the transformation between them. This algorithm, along with others, assume that the points recorded belong to a rigid body, meaning their relationship to one another in 3D space remains the same between frames. Another way to solve this frame-to-frame pose estimation problem is with an extended Kalman filter. By maintaining a state vector with all current observations and landmarks, the extended Kalman filter can be used to estimate the current position of the camera with minimal error. Once we have established these key points, or landmarks, we have to maintain some form of global map inside SLAM. One example implementation of this global map is a list of keyframes. Keyframes simply refer to images with their associated features and positions. Using these keyframes, we can perform loop closure when re-encountering a scene from an older frame. Another implementation of this global map is a list of circles. Circles, or surface elements, are small disks that dot the surfaces of objects in our scene. By using circles, we can also maintain a map of the scene that we've seen so far. The map is necessary for both estimating current poses as well as performing loop closures. What is loop closure? Loop closure seeks to answer the question, what happens when I come back to the same place I've been before? What do I mean by this? Imagine walking around a building. You start on the northwest corner of the building and slowly work your way around the building. Once you've completed the circle, you come back to where you began. However, due to SLAM drift, which is inevitable due to noise, we find that our estimated trajectory takes us to a position different from our starting position. Loop closure refers to the algorithms that detect coming back to the same place, as well as being responsible for optimizing the camera's trajectory such that the current camera pose realigns with our start position. One such implementation of loop closure goes as follows. We maintain a map of keyframes and their descriptions. This description is called a bag of words. Then, with every new frame, we compare it to all previous frames and look for matches using these bags of words. If we detect a loop closure, we optimize the global map to match our new observation. The way frames are described is using a bag of words algorithm. The idea behind bag of words is to form a description of a frame using a vector of words. Then, the similarity between two frames is how many words two frames share in common. The words assigned to each frame are created using patches of the image. If two images contain a similar region inside of them, that similar region will be assigned the same word in both images, increasing the similarity between the images. The final part of loop closure involves optimizing the global map. One way of doing this is by iterating through a global map of keyframes and optimizing them one by one. We know the current frame's transformation to close the loop. We can then use the updated landmarks to calculate the optimization of the previous keyframe. We can continue to do this inductively until we have optimized our entire map. This procedure operates under the assumption that the detected key points or landmarks are where they were observed. Unfortunately, in reality, there is sensor noise that contributes to faulty key point observations. Bundle adjustment addresses this by not only globally optimizing the poses of the camera at each frame, but also the key point observations within them. Although more expensive, this often leads to more robust tracking. One final augmentation to SLAM is provided via alternative sources of data besides just visual, in this case, inertial. IMUs, or inertial measurement units, measure acceleration. One common place you can find them is inside your mobile phone, used for orientation measurement and other purposes. Inertial data is very helpful for a SLAM algorithm, as understanding the direction of acceleration more tightly bounds the transformation between two frames. Now that we have these fundamental building blocks of SLAM, we can see how they come together to form a fully fledged SLAM algorithm. In general, SLAM is broken into two parts, with the front end involved with tracking the pose of the camera in real time, and the back end optimizing the global map of landmarks. In code terms, these are two separate threads running side by side at different frequencies. Modern day SLAM algorithms pick and choose a front end and a back end in order to achieve desired results of speed and accuracy. SLAM is an ongoing point of research, and several projects are striving to provide faster and more accurate pose estimation results. OrbSLAM 3 is one such open source project. It is a solely visual system with no inertial data used in its SLAM algorithm. BadSLAM features continuous bundle adjustment as its backend and differentiates itself from the others on the list by being a dense SLAM algorithm. Unlike a keyframe-based algorithm, BadSLAM keeps a map of each and every pixel and point observed by the camera, implemented as a list of circles. This results in a better performance in some conditions, but with heavier computational constraints, relying on a GPU to function in real time. OKViz features a visual inertial odometry system. This means that along with visual data, inertial data is used to perform SLAM. OpenARK SLAM system puts all these components together into a fully fledged SLAM system. It's built on several existing localization projects, OKViz, short for Open Keyframe-Based Visual Inertial SLAM, and DLoop Detector, a loop closure detection library. It is capable of performing real-time frame estimations from a variety of different cameras, using RGB images, depth images, and IMU data to accurately generate its predictions. The underlying OKViz localization system uses a tightly coupled visual inertial odometry system for its pose estimations. The loop closures use the iterative keyframe method described earlier, where keyframes are optimized iteratively using key points and ransack. There are quite a few open source libraries that OpenARK builds upon to create the system we have today. First, as mentioned before, we have OKViz and DLoop Detector, which form some of the foundations of OpenARK. Brisk is the key point extractor and descriptor used to featurize images. Eigen, series, and sweet sparse are all linear algebra solvers used throughout the system to solve optimization problems. OpenGL is used to visualize the result of the algorithm. dbow2 provides the bag of words functionality for loop closure, and PCL, a point cloud library, provides functions such as the 2D to 3D projection and ransack PNP. There are many parts to pick and choose from when putting together a SLAM algorithm. Adding bundle adjustment results in higher overall tracking quality, and tracking robustness at the cost of algorithm speed. Using a dense instead of sparse SLAM also potentially increases tracking quality at the cost of performance. With all these choices to make, it's important to understand the use case for your SLAM implementation. With so many parts to choose from, it's easy for a SLAM algorithm to begin losing efficiency to redundant data copies and transfers after incorporating too many different modules. This year's team at OpenARK focused on the code's efficiency. We removed inefficient and unnecessary data copies, resulting in a multiplicative speedup. Future work to OpenARK will likely focus on incorporating more of the SLAM functionality into our library and less reliance on open source libraries, a key step to increasing algorithm performance. To summarize SLAM, we have 3 steps that are performed continuously throughout the running of a SLAM application. A map of the environment in the form of keyframes and keypoints is constantly being added to and generated as more of the real scene is explored by our camera. The camera is localized at every frame within this map of the environment. And finally, loop closures are performed when returning to a previous point, re-optimizing the position of the camera and the map of the environment. The OpenARK SLAM team is constantly in flux as Masters of Engineering students come and go as the years go on. The lead graduate researcher behind OpenARK SLAM is Joseph Menke. The rest of the students listed here took part in developing OpenARK SLAM as part of their Masters of Engineering work in the last few years. Visit our website to see a full list of contributors to OpenARK as a whole. The final result is a SLAM demonstration where a set of 3 axes are anchored to the start position of the camera in 3D space, and the user is capable of placing objects at will throughout the scene, which will also remain anchored in 3D space, thanks to the estimation of the camera frame at all times. The code runs at 30 frames per second on PCs, laptops, and tablets. Alternative visualizations, such as bird's eye view trajectories, are also available. Coming up next, 3D reconstruction.